Okay, Unit 1, we learned about lift. You completed your project, came up with and discussed non-dimensional numbers, some important ones, Reynolds number, very, very important. Use that to help guide a model to a prototype. Now, what we want to look at is different forces. So we looked at lift, which is a very useful force for planes or anything that wants to fly. You're going to have the force of lift. Very, very useful. We want to look at now other forces that are going to be needed to be overcome, such as drag. Okay, so force of drag resists the motion of an object. So if I'm an object and I am moving through a fluid, in this case it's a gas, it's air, but there is going to be a force of drag that is going to be in the opposite direction of motion. It's going to resist the motion. So in a fluid, gas or liquid, the drag force is going to be due or is due to the viscosity. And we've performed demonstrations to see how different fluids have different values of viscosity. So different fluids will have different viscosities, which will have different effects of the drag force on that object that is attempting to move within that fluid or medium. The important thing is, in general, two major ways of studying drag force. So, again, in a fluid, the drag force is due to viscosity, but it's going to be investigated in generally two different ways. Or it's going to be modeled or quantified in two different ways. First is going to be pressure. Pressure drag. Drag due to pressure differences is going to be one way it can be modeled. So the first way or the first model that we can use is going to be, again, pressure drag. It is going to be development of a wake past a blunt body. It's typically not sensitive to a Reynolds number. So as Reynolds number increases or decreases, generally that is not going to affect the coefficient, which we're going to get into the non-dimensional number of coefficient of drag. It's generally seen in separated flows, and the shape is going to be called blunt. So what this is going to be is, let's bring our shapes and we'll compare and contrast. So this is our surface, our object that we have here. That is going to be, or this paper. And then we have the flow in this direction. And we want to represent the free stream as u infinity. That's the velocity of the free stream flow coming in. And the flow is going to be want to represent the area is perpendicular to the flow. So the area of this paper, flow is coming in, the larger surface area is perpendicular to the flow. So what you'll have is, you'll have the flow separating from the surface. So behind it, flow is going to go around. And you're going to see a pressure difference due to that. Think of you or me in a very, very windy day. If the wind is blowing towards me, this is my area, the wind is blowing in this direction. I'm going to have a force making it more difficult for me to walk forward. Pressure drag. The next is going to be friction drag. All right, friction drag. It is going to be again between a fluid and a solid. This is going to be represented by where you change the orientation of your surface. So now, instead of having the area perpendicular to the flow going into it, if we twist it this way where it'll be in plane, where we had performed our calculations on a flat plate for lift as different angles. So as you're completely 90 degrees, you're a bluff body. As you are 0 degrees in plane with the flow, you're going to be called streamlined. So the area is going to be parallel to the flow. So in between this, if we have our surface represented by the flat plate, and we have our flow coming in, again U infinity, what we'll have is flow going around that, and the flow is going to be separated, and you're going to get the development of a boundary layer. Boundary layer will go into a little bit later in later lectures, but right now the goal of this lecture is to understand how to quantify drag. And drag can again be thought of as modeled in two different ways. Pressure drag, bluff body, areas perpendicular to the flow. Friction drag, flat plate, the main area is in plane or parallel with the flow. Going to be represented by two different models. The coefficient or friction is going to be a function of Reynolds number. Bluff bodies tends to not be a function of Reynolds number. Alright, which leads to how we want to quantify drag. It's going to be very analogous with coefficient of lift. So, coefficient of drag equals the force of drag over 1/2 rho v squared a, where this is our force Force of drag. This is our density. This is velocity. Free stream. A is going to be the cross-sectional area. 1/2 is added for convenience. And this is going to be our coefficient It's going to be our coefficient of drag. And again, it's going to be determined experimentally. Perform your experiments, measure your force, put in the flow parameters, and you get a coefficient for a general geometry that you're trying to model. And then you can scale that up as well. So again, the coefficient of drag is going to be determined from experiments by measuring the force and different flow conditions. Coefficient will change with those particular flow conditions, again depending if it is going to be friction drag or as pressure drag. And will change with the shape as well as the angle. So let's go through and work on an example problem.